defined. Okay, that's not defined. All right, composition question number 2. I hope that you are already familiar with the first example. So we will just keep this one. Graphs and function. Graph and function. Let f be a function from the set A to set B. The graph of the function f is the set of ordered pairs. Okay, ordered pairs. Okay, I think this one I will just skip this one first because I have quite a long explanation later. So I will put it up in a different video. Okay, for graphs of function. Same goes to floor and ceiling function. Okay, floor and ceiling function, what you might need to remember is the table 1, some of the useful properties of the floor and ceiling function. This one is also I will put it up in the same video. Proving. Since majority of you is from computer science, we are not having very critical proving question and answer lah. So we'll skip this one. Factorial function. Okay. So just look at this example. As long as you know how to do calculation on factorial. See, if you have 2 factorial, 6 factorial, and so on, you will have the calculation. Okay, 6 factorial times every single element before 6. 1 times 2 times 3 times 4 times 5 times 6. And you have this one. It's easier if you just use scientific calculator lah. Alright, the factorial function. Okay, that's all under function. Then you finish with this function. I will continue with 2.4. Oops. Am I sharing the slide with you? Sequences and summations? Yes, no, yes? Yes, okay, good. Right. What we will have in this sequence and summation. So sequences, the examples, geometric progression, arithmetic progression, recurrence relations, Fibonacci sequence, and also summations lah. Some special integer sequences. So this the topic and the summation on special integer sequences give optional for us to cover on. Sequences. Sequences means the ordered list of the element. When we say list the sequence of 3 terms, means that you need to have that element. Remember that this one is not set. Okay, set, then you will use the term elements. But for sequences, we use the term terms. It's quite confusing, but when the question up in the test or exam, you may differentiate lah between sequences or sets. Okay, sets we use the term elements lah. The list of the value in the set we call element, and the list of the value of sequences we say as terms. Okay, and the second example is infinite because we don't know when to stop. Okay, it's infinite. It is countable. Countable means that the number is exists. 1, 3, 9, 3, and also something else over there, but it's infinite because there's no stop in the list. So that's why we just continue with the ... Sequences arise throughout maths, computer science, and in many other disciplines ranging from botany to music. Why we use botany and music? Because these are two total different things. You can just use cooking and engineering. It's up to you. So this is the book. So it's up to them to use botany and music. All right, we will introduce the terminology to represent sequences and sums of the terms in the sequences. Definition. A sequence is a function. I cannot see it from this slide. Sequence is a function from a subset of integer. Okay, integer, usually either the set 0, 1, 2, 3, 4, including 0, or exclude the 0, right, to a set S. So this is the only the example. Okay, you may use other name of the set. The notation AN is used to denote the image of the integer. What is this image? Means that the codomain, or more specific, it's a range, right? Image of the integer n, okay, of the integer n. Remember that the sequence is basically take care or use the location of the sequence, the location. So this is the first number, the second number, the third number, fourth number. So this is what we call the locations of the range or codomain. We can think of AN as the equivalent of FN. Okay, we can think that way because this is what is the value of codomain, or more specific is range. It's a function from 0 to infinite number. So that's belongs to set S. We call AN a term of the sequence. A term of the sequence. Why? Remember that when we have the n, means that the number of how many terms in the sequence, right? Term, okay, not the element, because we use sequence. Okay. So example, consider that the sequence AN, the same style of us when you want to write sets for sequence, where you have a, a, a curly bracket, right? A closed curly bracket, where you list down the sequence element, the sequence terms within the curly bracket. Okay, now where you have AN equal to 1 divided by n. Remember that before this, you can also think of AN as Fn, right? Right. If you want to think like that also can. So Fn, which is the range of the function. Oh, sorry, the range of the function. But this is the list of the range. All right. Now you have AN equal to A1, A2, A3. So this is where the value, the value, and this is the n. Okay, the n value, which means the location, the first location, second location, third locations. Okay. 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 So these would be the initial terms. Usually we use A naught. Okay, A naught as the first term, or you can also have A1. Okay, if you start with A1, the second one would be A2, A3. But if you start with A naught, the second will be A1, A2. Okay, usually people love to use this list lah, because it's easier to see the number, right? If you start with 0, then it's quite confusing when it comes to the next numbers. Right? So, but this one is highly depend on the questions that if it's asked and then use different number of the initial value, then you have to be very careful on this. Okay. Okay. Geometric progression. A geometric progression is a sequence of the form of a r square until a r power of n, where the initial term a and the common ratio r, initial term a, this one, initial term a, and common ratio r are real numbers. Okay, so usually we use real numbers. Okay, example, let a equal to 1. Okay, this is the initial term, and R as the ratio equal to -1. Then what will you have for list of Bn? Okay. Remember that when you have B not, means that it is equal to A, B1 will equal to A up to A. 2 AR3. Okay, because it is depend, if you see, the power is depends on the n value. So this one is initial term A and common ratio R, and then when you see the style of calculation in the list, it's add up by 1 for the power of R, and you will have the list. Given that B naught equal to A, where A, the initial value as 1. So we just write it back as 1. For the second one, we might have B1 equal to A, which is 1 times -1 square. But why is it negative? It's supposed to be 1, right? Okay, let's check. Oh, okay. I just see, oh, AR. So the form is different lah. So it should be like this lah. AR, AR2, like that. AR3. So everyone agree, yeah? Okay. So just erase everything here.
In the first term, the A is alone because the R next to it is to power of 0. So anything power of 0 is 1,
Yeah,
right?
yeah. Is it correct if we use the geometric progression, it's missing AR, right? Yes, okay. Another one is agree. So A is equal to A. So A equals to dia. Hello? Excuse me, Shasha. Oh, my. Excuse me, Shasha. Shasha, please. Okay, we will continue later. Shasha, excuse me. Excuse me, Shasha, are you in front of your computer? I think I can mute everyone, right? Here? Oh, okay, Sasha. Thank you very much. Okay, we continue. So 1 times -1 means -1. And this one is AR power of 2. 1 times -1 power of 2 means 1, and so on and so forth. All right. So there is a mistake in here lah. So we use the list of this. And example number 2, number 3, I hope that you can just go through by yourself lah. Example number 2 and number 3. Okay, arithmetic progression. This arithmetic progression is a sequence of the form of a plus d, a plus 2d, until a plus nd, where the initial term a and the common difference. Just now we use a common ratio, right? So for arithmetic progression, we have common difference d is again the real numbers. Okay, example number 1. Let a -1 and d equal to 4. So when you have s naught and z equal to a, now you're confused already. Yes, the answer is wrong. Okay lah, we just use my version because the slides is just directly taken from the sample slide lah. Alright, S4 -1 is 1 to a plus d is that -1 plus 4 means 3. So the answer is wrong. Huh? So S2 a plus 2d means -1 plus 2 times 4, 7, and so on. Okay, so the answer 1, 3, 2 is 7, and so on and so forth. Alright, then you can try yourself on example number 2 and number 3. As long as you know how to get the style of getting the geometric progression and arithmetic progressions is okay. Okay, next, string. A string is a finite sequence. Finite means it will have the end, okay? Have stop lah. Stop of characters from a finite set alphabet. Okay, because the set is well known already and you will have the alphabet set, finite alphabet set. Sequences of characters or bits are important in computer science. Yes, when we do programming, we may need the characters or we call it bits. The empty string is represented by lambda as the string that has no terms. Okay? Lambda is the string that has no terms. Empty string has length 0. No terms and the length is 0. So the string A, B, C, D, E has length of 5. Length of 5. If let's say the question is regarding string, just now is using numbers. Numbers, we don't use length. Numbers, if it is numbers, we use terms. If it is string, use length. Okay. Recurrence relation. A recurrence relation for the sequence an is an equation that expresses the an in terms of one or more of the previous terms of the sequence, namely a0, a1 until an minus 1 for all integers n, with n greater than or equal to n0, where n0 is a non-negative integer. A sequence is called solution of a recurrence relation if its terms satisfy the recurrence relation. The initial condition for the sequence specify the terms that precede the first term where the recurrence relation takes effect. Okay. imagine that when you have a sequence, okay, a sequence A0, and then you have the value, and then A1, then you have the value. What if the question asks you to identify what is the value of A101? Are you going to calculate every single step until you get this? No, right? So this is where you need solution. Okay, you need solution. When you have the solution of recurrence relation, the recurrent relation means that the relations of this recurrence in the sequence, then you can solve any numbers of n within the sequence that it has. Right? It's either 101, 2000 or something. Whatever n that is asked for you, then you can solve it as long as you have the solution of that recurrence relation. Okay.
Solution is the formula.
Sorry?
Solution is
This,
solution is the formula that we put in the n number of
yes.
n to
Yes,
get
the
out
formula. Yes,
okay.
Hazmi. Yes, that's the formula. So the initial conditions for sequence specify the terms that precede the first term where the recurrence relation take effect. Right. Let's look at the example number. All right. Example number 1. Let an be a sequence that satisfy the recurrence relation of n minus 1 plus 3. For n equal to 1, 2, 3, 4, 5 until you don't know when it stops. And suppose that a not equal to 2. Okay, the initial condition. So this is we call initial condition. What are A1, A2, A3? Right. We see from the recurrence relation that you may have A1 equal to 5 because you already been given the initial conditions which is 2, okay, 2, and that's just simply plus 3. Okay, then you save this answer as A1. And then what about A2? A2 means A and minus 1 means this one should be A and A1 lah. A1 plus 3. So A1 getting back from the previous answer is 5. So 5 plus 3, 8. A3 which means equal to A and minus 1 means A2 plus 3. A2 get back from the previous answer means we will have 8 plus 3, 11. So this is basically the just solution for recurrence relations. Okay, now so that's only the solution for the what that you having from the given relation. Okay, later will be solving the recurrence relation, means that finding formula. Now I continue with this. Example number 2. Let an be a sequence that satisfy the recurrence relation an equal to an minus 1 minus an minus 2 for n equal to 2, 3, 4. And suppose that the initial condition is a it is 3 and a1 is 5. Okay, it gives you two initial condition a0 and also a1. So I think this one just can skip this one. I wanted to show you the more important thing. For Fibonacci, define the Fibonacci sequence F0, F1, F2 by initial condition. One initial condition is given F0, F0 equal to 0, F1 equal to 1. So the recurrence relation is this again, same lah. Okay, when you want to get the current F, for example, F6 is that F5 plus F4. So we'll get the list of the solution. Now, solving recurrence relation. You are finding a formula. This is where you are solve the recurrence relations. Okay, finding the formula for nth term. Okay, nth term. Where when the question asks you, oh, okay, find the term of A101. So it is not good if you just having the recurrence relation and then you just calculate one by one until 101. So the times will be up in minute. Of sequence generated by a recurrence relation is called solving recurrence relation. Such formula is called closed formula. So this is just a term lah for in this topic. Okay, various methods for solving recurrence relation will be covered in chapter 8. Oops. Where recurrence relations will be studied in greater depth. So this under this subtopic will be introducing how to find the formula for recurrence relation. Okay. First one, the first example, iterative solution. Example 1. Working upward, forward substitution. Let AN be a sequence that satisfies the recurrence relation AN minus 1 plus 3 for N 2, 3, 4, and suppose that the initial condition is A1 equal to 2. And that it will have A1, A2, A3, and so on until A4 kan. So A2 okay, A2 here. When you are finding A2, see the recurrence the relation of AN is A, the value of the previous A is that 2, means that this one is A1 is equal to 2, so 2 plus 3. Okay, and then A3 again it is taking the same value or formula from the previous one, means that A2, and then you plus with 3. Okay, so means here when you look at this, you may rewrite it as like this: 2 plus 3 times 2. What about A4? A4, when you have 2 plus 2 times 3, okay, plus 2 times 3 means that from here is just rewrite it like this lah. Okay, it's same thing, right? 3 times 2, 2 times 3, 2 times 3, and then again plus 3. So you may have 2 plus 3 times 3. Okay, just rewrite. This one is also rewrite. Until you see the pattern, okay, until you see the pattern where you see the pattern here. See, this one is A4. The N is equal to 4. This one is equal to 3. See the pattern here? A3, the N is equal to 3. And then here is 2. Okay? So, when you see that pattern, it may comes to 2 times 3 times the previous number of N. When you will have like A N here, for example, if you want to find A6, so means that 2 plus 6, 5. Then you get the answer. Okay, So there are some patterns. So some students or they ask me how to find the formula. It is basically up to the it might have it might produce two or more formula actually, as long as the final one, the final formula that you get answered every answered the give the solution for the sequence correctly. Okay, so this is the style of this example. Just rewrite it again until you get some pattern in there, then you might have this one. Okay, have the solution. We'll move to the other um, for the other example. Working downward, backward substitution. Let AN be a sequence that satisfies the recurrence relation. AN. Is this the same one? Same thing. Sorry. Financial application. Okay. Suppose that a person deposits 10,000 in a savings account at a bank yielding 11% per year with interest compounded annually. How much will be in the account after n years? Let Pn denote the amount in the account after n years, Pn that satisfies the following recurrence relation. And you have these recurrent relations with initial condition PO 10,000. I actually have already done the paper. I've already prepared to calculate this. But since I cannot show you the video, it is hard for me to write every single thing. So I will try my best to show it here. Let's check the time first. 12:45.
Ma'am, you can take a picture of it.
Sorry?
You can take a picture of what you draw and
Yeah, I think so. Yes. Yeah, because
and
this one is basically the same thing that just now. Just it apply on the um, financial area. Okay,
uh,
right. This keep special integer. This one is op as well. Um, this, okay. So for summations, again, I will record a video on summations, the function just now, and also continue with summation because we need to go to exercise. Okay, exercise. Now, imagine that you have, this one is under summation only, class activity. Okay, now class activity 2. So this is for the sake of taking your attendance. So if you look at the e-learn, I've activate the link for submission of week 2 class activity. So this is very basic question 1, just to take your attendance. All right. List the first 10 terms of each of these sequences. A, the sequence that begins with 2 and in which each successive terms is 3 more than the preceding term. B, list the 10 terms of the sequence that lists each positive integer 3 times in increasing order. Okay, 3 times in increasing order. And C, the sequence that lists the odd positive integers. Odd positive means what? 1, 3, 5, 7, because it's positive, right? Integers, including negative and positive integers, right? In increasing order. Increasing order means um, yalah, increasing order. Listing each odd integer twice. Okay. So you can just type your answer in the submission link. Then don't forget, just write the sequence. Yes, just write the sequences. Yes, thanks for the answer. Thanks for the question. Hmm. I need to test again on my camera so that I can share the full screen with you guys. I really hope I can do it as soon as possible because I have tried few times with numbers of participants and it worked. Um, I hope it will work after this. It is easier if you use pen and paper in a traditional way to show the calculation. No need, just write the sequence of this. No need in the curly bracket. Ibrahim Ajami, yesterday attendance have been taken during the class activity that I posted. Yes, write the sequence only, proving for proving. Zehui, this for this question we don't have the initial term. Okay, we don't have any initial term. This is only under the first subtopic under sequence. You need to write the terms according according to the questions. Okay, for example, question A, you have to write the sequence that begins with two and so on. Okay. Ibrahim Ajami, you didn't do yesterday class. Did you read my message on the e-learn and as well as on the forum? I opened the class activity until 5 p.m. yesterday. 1 1 2 2 2 3 3 3. Yes, for B. Correct. Three times. Correct. Neo Min An. Correct. C, the sequence that lists the odd positive integer. And you need to list it twice. 1 1 3 3 5 5. That's the answer. Okay, have you done this? Okay, for those who have finished this, there are few. I have also uploaded the announcement on the assignment one. Okay, I really apologize for those whose names were not in the list. So I've already rectified it. I already updated the list. But still, if your name still not there, please email or message me in the e-learn so that I can rectify or update the list for you. Okay. This happened is because mainly because the list that I've got from the CLA means the name list from the university, and also the list name that we have here in computer science. Some students, register through computer science, maybe because they are repeating the subject, maybe because they are from other course and change to this computer science, and also they are taking this as minor subjects and so on. So that's why it not perhaps it did not updated on the USM list, or did not updated in the CS list. So that's why the problem occurs like that. So whatever list that I have in hand, that's I have been informed that they updated one. So I just creating grouping you guys using the list that sent to me. Uh, yeah, and when I receive few emails from some of you, then I realized that few students missing lah in the list, so I apologize for that. That was my bad. Okay. Assignment, use Microsoft Word or Office. You can use anything that you prefer. Okay. Chapter 1 self-study questions. No, I'm afraid to give it because I also did do it myself. So I don't know whether the list of the answer is correct or not. I can give it. I can upload it, but please bear in mind that the answer is actually provided by the questions lah, by the book that I take somewhere. So that's from my question bank. Right? I don't have that much time to do all 200 questions. The question C means double the odd positive. Yes. There are also some students who are exempted from this course getting into the name list of the assignment. For those exempted from this course, the name their name is still active. So that's why their name is in the list. Okay. So that's not my, I don't have power to remove them in the e-learning. So let's wait for e-learn to remove them. Lah. So children, the number, the name is still active. Okay. Group has only 3 members. Yes, please proceed with group with 3 members. If you do have only 2 members, then you come to me and ask. Okay, because few members left the course, and that's why your group only remain 3 members. Okay, 3 to 4 members is okay, but not 5 is too much. But not 2 as well as too small. Ibrahim Ajami. Okay, I will try my best to rectify your case. Chapter 1 from me, and at least discuss the question. Okay, chapter 1, if you notice that chapter 1 is basically just to introduce the basic terminology, and also the symbols. Okay, that's not more than that. So the reasons why I put up chapter 1 is basically just to refresh your memory on I believe that one is already covered in form 5 ke? Form 5 or diploma or matriculation, STPM somewhere. Just to refresh your memories on the symbols and also terminology. Not more than that actually. Because if you look in depth into chapter 1, it is a lot to cover actually, right? So if you do have time, you can do the exercises. But if you don't, at least you can look back at the notes if you find difficulties in the terms and terminology in the rest of the chapters, chapter 2, chapter 4 later. Right? All right, Ryan Rashid, you and Beja have sent email to Intan Rahana student.usm. All right. My my staff my staff email is intanrayhana@usm.my only. Right. Not at student. Okay. Please recheck it again and forward the email to my real staff email. Okay. Metric was totally easier than chapter one. Alam. Okay, for those whose name is not in the list yet, please email me back. Can you please email me back your name, your metric numbers, and also your email, your student email, and also other emails if you have. Arya Diva, all informations on the group assignment has been up in the e-learn. You may need to download everything in the folder, then you may know, right? Yes, chapter one is not included in final exam, but the terms and the terminology and the symbol will be used in 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 the other chapters actually. Yes. Okay lah. I think that's the end of our meeting. 12:59 already. Thank you very much again for you who come to my class and wait until the end. And I hope that everyone success in your study, and please take care of yourself, do not go out, stay at home, eat at your room. Right? Okay, bye. Assalamualaikum. Take care, everyone.
Ma'am, do you have a minute? Slang, ma'am.
Yes, wait a minute, I will take
Ma'am, I'm actually Redwan Afsar. I sent you an email, but I did not get any reply. I had a surgery on 2 days ago, so I want to talk to you about that. If you have a
Redmond,
minute.
okay. Sure.
So, ma'am, I actually have two confusions. One is like I sent you an email for me to request you to put me in a group B for the lab. I don't know
Okay.
what is the status of that. And yesterday, found out that they put me in group E. So I was thinking, should I follow group E or group B for the lab? That's question one. And the second question is, I could not find my name in the even in the updated list of the group assignment, ma'am.
Um, are you international student, right?
Yes, ma'am. And also, I postponed. And actually, I just had the surgery 2 days ago, so my condition is really bad. I have problem while talking to you because my blood is coming from my nose. So, ma'am.
Okay. Okay,
Okay, so
for international student, every international student is actually grouped in group E,
okay,
not
ma'am.
E. Okay, group
Okay,
E,
ma'am.
just follow group E. Okay, since that, according to my message earlier, since that we are unable to get TA, teaching assistant, so that we need to rearrange back our tutorial slots.
Okay, ma'am.
That means we will run this tutorial slot asynchronous. Okay, means that I will upload the video on the answer on the selected answer that I think is important for you to know the steps of the solutions. And also you need to upload your answer and solutions in the given link
Okay, ma'am.
of that particular week lah, of the tutorial. So
Okay,
that's
ma'am.
how we take.
So,
That's
ma'am,
how we take attendance.
in this regard, I had a question like, so if this is going for the asynchronous, so in that case, is it going for like a lecture class, like instead of 5 or 6 slots for the lab? So, are you going to have a particular day, particular time for the
Uh,
or
no, when I have discussed with Dr. Sukuma, and he said that it is not fair for other students who cannot come at that class. So we decided to just upload the video on the solutions, the selected number of solutions lah for the tutorial. So
okay, ma'am. My question is like, when will be the class? So are we going to stick with the same lab for everyone? Like, it will be asynchronous. I understand, but what about the time? Like, should we follow the say the group E is supposed to be Monday 1 p.m. So
uh,
are we going to join that class or that was my question. So are we
okay.
are we going to have 5 or 6 slots or?
No. If it is say asynchronous means it is offline. Means
Okay, ma'am.
it's offline. Okay.
So there
So
will be no particular time. It's just
no, yeah, no.
okay, ma'am. I
No.
understand, ma'am.
So
Understand, ma'am.
just please make sure that you at least you spend 1 hour to focus on the tutorial at least,
Yes,
because
ma'am.
we already don't have the online session, so that
Yes,
you
ma'am.
have to push yourself lah to at least 1 hour per week, all right, to focus
Okay,
on
ma'am.
the at least watching the video that will be uploaded soon.
Okay, ma'am. And
Okay.
about the assignment list. So are you going to update it by today? Because my name was not in there.
Yes, I will. Because
Okay.
this morning I've updated. I thought that one is the latest version one. So I missed
Okay.
few students again. Right.
Okay,
So
and ma'am,
sorry about that. Huh?
I'm actually really sorry. You have a child children, and you need to take care of him, and I'm just
Yeah, yesterday I really,
yes,
yesterday it
yes,
was
ma'am, I
a
understand.
very terrible day for me, because it's just happened in the morning, 8 a.m., and then the nursery did not accept him to
Yes,
join
ma'am,
the
I understand.
nursery, lah, with the SOP and all that. So yeah, I have to deal with that.
No, ma'am, because ma'am, just 2 days ago I had the surgery, so I understand the health issue more than anyone else. So, ma'am, I just want to clarify again about your email. Is it internraihana@usm.my, right?
Yes, yes.
Okay, ma'am. So, ma'am, I'm just sending you an email about my health issue, and should I need to send
Sure.
you the medical certificate, like the discharge certificate as well?
No, just email me.
Ma'am, because the doctor prescribed me to stay in the bed for complete test for 15 days. So, and the other lecturer told me to send them an email just for the record. Ma'am.
Okay. But as long as you can, you can
Ma'am, I
attend
can
the
just
class.
I can attend the class, but I think it will take me like 1 or 2 or at least 1 week to just dressing just to on the heels, ma'am. So
Oh,
I just need to lie down on the bed because if I wake up from the bed, my because it was a nasal surgery, so blood comes down from my nose, ma'am.
I see.
So
Okay.
yeah,
So
yeah.
in case you just give me the document as well. All right.
Okay, ma'am. Thank
It's
you, ma'am.
okay
So, ma'am,
about
I'm
that.
sending you an email, and also I am CCing Dr. Sukumar
Yeah.
as well.
Sure,
Okay.
sure. Yes. That
Okay.
is
Thank you, ma'am, for your
no
time, and sorry
problem.
again for
No
bothering you.
problem. No
Okay, ma'am.
problem.
Assalamu alaikum. Assalamu alaikum, ma'am.
Waalaikumsalam.
Excuse me, doctor.
Yes.
May I ask? Currently, I'm in a group of four.
Yes.
One of the participants is currently missing from the email contact group.
Okay.
So, at the same time, I looked through the CPT 112 participant list in the e-learning website.
Uh-huh.
They are also missing as well. So, should I assume that they are missing? They have quit the course, or should I assume that they're still around?
Are you the one who emailed me about this? The missing person? The missing email?
Yeah. Her name was Nur Najiha something, I think.
Nur Najiho.
Yes.
Okay, can you did you email me on this
Yes,
before?
I did.
Oh, okay. Let me check my email again. I think
Yeah.
I think I have read your email on the missing student.
どうし、
そりゃこっちのセリフだろうが。
平成なくば自由もな。団長たちが、
いやいや、さっきまでそのたくちょ
トリックオアトエルモートちゃん。ハロウィンも近いことだ。
うん、
これでエルモートちゃんもやいやと
なるほど。未熟は挑まぬ理由に、
はあ、いやいや、
リベラ殿より賜りし教訓、百分は一見に許せ。どうだ、
死んだ。
そうか。
ここまで不気味じゃねえだろ。
エルモートちゃん。
おう、
すごいの。
そうか。
タントちゃんのお化粧したエルモートちゃんは
そうい
お仕置きしちゃうぞ。
誓いの剣をその身に受けよ。
水着の美少女が癒したパーティーさせないもん。
はあ、誓いの剣をその身に受けよ。
ないない。
守れなかった。
うちの子い高すぎるぞ。頑張り時やで。一緒に全力や。逃がさへんで。お尻決戦やな。どないよクワマグナ。
ない。
バカな。覚悟はいいか。
水着の美少女が癒してやるぜ。
はあ、これで決める。
どないや。
はあ、でやでや、隙だらけだ。そこまでだ。
お仕置きしちゃうぞ。 ないどきな
マイ乗れ
こんな水着の美少女に
隙だらけだ。メイン準備はいいか。はいよランちゃん、俺たちのコンビネーションを見せてやろうぜ。気合全開だ。いいぞベイン、メイン今だ。サンキューランちゃん、行くぜ。
マイマイ
やっぱランちゃんかっこいい。見えた。バイスフリーズル。隙だらけだ。チャンス到来だぜ。よしぶちかませ。レーベバインや。僕が引きつける。幾千の夜を愛を僕が引きつける。
お仕置きしちゃうぞ。水着の美少女が癒してやるぜ。
誓いの剣をその身に受けよ。
水着と思って侮るなよ。
はあ、そこまでだ。これで決める。ソーレディ・ベローナ。誓いの剣を
アクアマグナ。
バイス・フリーズル。動けない。
どきな。
はあはあ、隙だらけだ。
どきな。
マイ
隙だらけだ。大丈夫、俺を信じろ。
マイ
まだ引くわけにはいかない。
水着の美少女が癒してやるぜ。
遅いバイス・フリーズル。隙だらけだ。大団円のラストへ。はあ、これで決める。ソーレディ・ベローナ。誓いの剣を
水着のうちの
任せたぞ。
さあ逃がさへんで。頑張り時やで。一緒に全力。お尻てっぺんやな。
そこまでだ。どうだ。死ぬ。はあはあ、隙だらけだ。どうだ。死ぬ。遅い。
マイ
はあ、覚悟はいいか。 守れなかった。メイン準備はいいか。ヨーランちゃん気合全開だ。いいぞメイン今だ。サンキューランちゃん行くぜ。ヒーロー見参ってな。
すっごいのお見舞いした。
ここから攻めるぞ。よし今だランちゃん隙だらけだ。
赤の舞林縁改め、これにてしまいや。
for your response. We will start shortly, yeah? Okay, I will be unsharing the attendance QR code shortly. Those of you who are not in time to scan the code, we will do it later after the lecture. Okay, thanks. Okay, good afternoon, everybody. Today, we will try to tie up topic number 1, which is the introduction section. Where we left off, we were basically talking about the evolution of computers ranging from the first generation, the vacuum tubes, okay? Then second generation is the transistors, right? And then the third generation, we were talking about the integrated circuits. And you saw how those transistors or components are then etched onto those silicon wafers, all right? And all the circuits are all very, very minute at a very, very microscopic level. And of course, the number of transistors that have been packed onto a single chip has been increasing every year. And therefore, in Intel, one of the founders, by the name of Moore, he has proposed that the number of chips the number of transistors being packed onto a single chip is doubling every other year or so. All right. So I think we're going to try to tie up this particular topic today. In fact, there are still quite many few slides, but the message is actually very short. So I think I will just go through very quickly, all right. Okay, so now let's look into the different processor families that are popularly available today. And we'll just do a little bit of history as well. So we start off with the x86 machines, or rather the x86 chips. Started off back in 1974 with the 8080, and then again, it has evolved over time. After that, 8086, then the 286 machines, okay? And it evolved from 8 bits until 16 bits and so on and so on. And with the number of increasing bits, that also means that the addressable memory is also increasing, okay? So the more bits the architecture has, the more larger memory space that it can address, okay? Then 85, it went into 386, okay? And then, of course, by the time this idea about multitasking also came about. Multitasking means it can do many processes at the same time. Back in the older days, the computer can only run one process. For example, let's say if you're only for example, if you're doing a Microsoft Word, you can only do Microsoft Word. You can't do anything else. Okay. But now, of course, with multitasking, you can run Microsoft Word together with your browser, together with your other stuff running all at the same time. Yeah. Then after 386, then came 486, and then with 486 also there's this idea about pipelining and all these powerful caches all came into play. And not only you have the ALU, but in the 486 they also have a math co-processor as well, which means a dedicated processor for mathematics and stuff like that. Then with the Pentium machine, they broke away from the the 386, 486 kind of numbering, but they call it Pentium. And then that also introduces the super scalar kind of processing. That means not only pipelining in which all the stages are packed onto one another. Super scalar also means that it's doing all the stages in parallel as well. Okay, so that is the Pentium machines. Then again, the evolution grows: the Pentium Pro, Pentium 2, Pentium 3, and so on and so forth, with increasing complexity, increasing capabilities like 3D graphics, audio and video processing, and so on and so forth. Okay. Then you have Pentium 4 in the year 2000, and then after that we have the Core series of machines. All right. So they broke away from the Pentium the naming, and then they call it the Intel Core processors. And then that was one of those first dual core machines. Okay. Then later they evolved into 64-bit processors, and then from there we have also Core 2 quad machines with 4 processors on a chip, meaning 4 cores, right? And if you notice that the number of transistors are mind-boggling, even at that time, more than 12 years ago. Okay, already 820 million transistors packed into that small little space. Yeah. And then from this particular slide, we can then see an overview of the processors over the years, ranging from the 4004, the very, very first Intel commercial chip back in the 70s. It's just only a 4-bit machine. And then eventually it evolved into, the x86, then 286, and so on. So it's getting more and more complicated. As you can see, it will then increase in terms of the number of bits, increase in clock speeds, okay, increase in the number of transistors, and so on. Okay, so I think this also you can see from the textbook, and also you can see from many resources online as well. You can see how the chip has evolved over time. All right. Yeah. So, but basically, the x86 machines are pretty dominant outside of embedded systems. Outside of embedded systems mean that built for desktops, built for laptop machines, built for servers, and so on. This x86 architecture is not so popular for processors in washing machines or processors in cars, for example. Okay, so they are not meant for embedded machines, but they are meant for computers, desktops, and things like that. All right. So yeah, so that's more or less the x86 series of computers. Aside from the Intel machines, once upon a time, IBM and Apple, they also have their own series of processors as well. But now I think they have stopped making machines based on their architecture. But once upon a time, this PowerPC architecture was also very popular. And the PowerPC is basically a RISC machine, RISC, meaning it is a reduced instruction set computer. Now, remember earlier on we talked about instruction sets when we talked about architecture, remember? So in these PowerPC processors, they aim to have fewer instruction sets, okay, which means the instruction sets are more primitive, but they capitalize on the limited instruction set, meaning to say that it can potentially run very, very primitive instructions, but faster. Okay, so that is the idea behind having the RISC machines. And so again, they started way back in 1975. Then they evolved over time. Okay. So they came up with this PowerPC architecture. IBM and Motorola and Apple, they joined together to produce these machines. And the early machines, the early processors were called the 86,000 machines. Okay. So again, it's superscalar RISC, and that's also how the Apple Macintosh came about, using the PowerPC processor. And yeah, these are the evolution: 601, 603, 604, and so on. So yeah, again, they evolved from 32-bit machines. Also predominantly a desktop kind of usage. Okay, and also for servers as well, right? Then eventually they also have processors for servers, and by that time also the 620 are also 64-bit machines as well. Okay. After the 601, 603, 604, 620, then they changed the series into the G series, G3, G4, G5. Okay. And even back then they were already using 64-bit architectures already. Okay. All right, so that is the PowerPC. Next, we're going to talk about the embedded systems chips, okay? And a very popular architecture are those developed by ARM, ARM, right? And ARM also uses a RISC design, a reduced instruction set computing design. And their chips are mainly used for embedded systems. Okay, embedded systems means, like for example, if you have a car and you have this IC chip under the dashboard to control braking, control fuel injection and all that. But the main controller there is an ARM processor. Okay, so the ARM processors are very popular for such usage. Okay, in cars, in electronic devices like washing machines and security devices and things like that. Okay, so the ARM processors are usually not for desktop machines or server machines. Okay. So they are mainly used within a particular product, and usually their purpose are actually very dedicated. It's not for general purpose processing. Notice like for the Intel processors and the PowerPC processors, they are in a computer machine, and that computer can be used for anything, right? You can use for gaming, you can use for calculation, you can use for word processing, general purpose. But for the ARM processors, usually they are more dedicated. Okay, like for example, on the slide here, you can see anti-locking brake systems, okay, or some fuel injection system. So their purpose is usually more specific lah. And of course, being embedded into a particular product, they have to come in different sizes and optimized for different use. Okay, and of course, different requirements as well, according to, let's say, safety requirements, lifespan requirements, more harsh environmental conditions. Imagine if a processor needs to be put into a car, and that car is left in the sunlight for a long time, so it has to be durable enough to withstand certain harsh conditions, right? And also, available in different speeds. If you want to have a ARM processor to process braking data, your processor better be very, very fast, because it's a life and death kind of situation. You brake and then you need to process it immediately, right? As opposed to maybe using the processor for something that is less critical, maybe in a washing machine or something like that. So that processor doesn't have to be very fast, right? So it has to have different. It would then need to be. It then need to suit different purpose, different demands. Okay. So the organization of how the embedded systems work will probably look something like this. Okay. So right in the center you have the processor. Probably an ARM processor, and then look at whatever is outside of it. Okay, you have some software, some memory, but you have also other things like the human interface, actuators, because sometimes the processor need to trigger a mechanical device to move. Okay, so that's how the actuators work. The processor will also need to control, or rather get input from various sensors. All right, so if you have a braking mechanism, so it needs to sense that the brake has been applied, how much of friction is being generated, and things like that. So the ARM processor needs to be able to connect with all these sensors as well, right? So this is roughly how the environment of the ARM processor works lah.
Victor, can you repeat the actuators?
Actuators are moving devices. Like for example, if okay, one example is, let's say if something happened, you want something to move, for example. So actuators are devices that can move. Okay, open, close, or move left and right. Those are actuators, and usually comes with a motor. Okay, so when the motor is driven, the device will move. So those are actuators, okay.
Thanks. Got it.
Right. Okay. So those are the three popular family of processors, which is the X. It's a mouthful a bit. X86 machines, the PowerPC machines, and also the embedded systems ARM processors. Okay. And of course, again, those three are have specific purpose. And but one thing that's important from all these processors is that they have different purpose, different series, because it's a family, right? It comes in a series of processors. One interesting thing about the ARM processor is that it is very popular in the deployment of IoT technology, okay, Internet of Things technology, okay, and this is where smart devices come in, smart appliances, and and a very popular devices that go together with ARM processors are the sensors. Okay, sensors. So in future, maybe when you think about your projects for your second year or your final year, maybe you can think of an IoT kind of project which uses various sensors. It can be a very innovative kind of project, right? And then you can develop an embedded system for your final year project as well. Okay, so a little bit more detail about the ARM processor. So it's basically high speed, very small size, okay, and very low power consumption. So imagine if your ARM processor is being used in, let's say, a mobile phone, or maybe in a car, for example. You don't want to have constant power supply to that particular processor. So it can work on a battery, or it can work on very low power consumption environment. Okay, so that's the idea behind the embedded systems ARM kind of processor, right? And of course, yeah, it's very popular in PDAs, mobile games, mobile phones. Okay, and yeah, it was developed back in the 80s itself, more for the embedded machines. Okay, and of course, you have a wide range of ARM products. Okay, now the three popular categories of products is the Cortex A, Cortex R, and also Cortex M. Okay, and even within those categories of products, again, there is a lot of evolution. Even the Cortex A is A5, A7, right until the modern, the recent A77, A78, and so on. Similarly, for Cortex R and Cortex M, again, the evolution is very quick, and the processing power is really impressive. Okay. Okay, the diagram here shows a little bit more of a detail on how the ARM processor is located within a particular device. So the top part of the screen is a microcontroller, maybe in a car, for example, or microcontroller in a washing machine, or microcontroller in, I don't know, some appliance lah. Okay, so that microcontroller has all the other stuff like interfaces, I/O ports, and all that. But if you look at the bottom right of the screen there is an ARM processor. Okay. Now, what is inside the ARM processor? Well, again, inside the processor is pretty much the same as all the other diagrams. You have the ARM core, which does the actual processing, meaning it contains the ALU and things like that. And all the other stuff like the memory and the bus and things like that. So whatever is in the traditional processor, meaning the four functions, remember, you have the storage function, the processing function, the interconnection function, and also the I/O function. It's all it's very similar as well. Okay, so but this one just gives you an idea on how it's being positioned in a microcontroller for a particular device out there. Yeah. Okay. To end up this quick section on the three different families of processor, I would like you to do a very quick research. Okay, a very quick research. I want you to go to eLearn. Okay, just a minute. I want you to go to eLearn. I will activate the thing now. I will also give you a code on the chat box. Okay, so you can either go to eLearn or you can look at the chat box. There's this thing called quick research. I want you to quickly find out what's the difference between Cortex A, Cortex R, and Cortex M. Okay. Now answer in the eLearn. Answer using the link in the eLearn. It will open a forum. You create a discussion thread and you key in your findings. Okay. Don't put in the chat box. Put it in eLearn. Okay. A quick research. What is the difference between Cortex A, Cortex R, and Cortex M? Okay, so quickly do now. I'll give you maybe 3 to 4 minutes. Do a quick Google search or whatever. What's the difference between the A, R, and M series of the Cortex processors? Okay. To answer the question, you can add a new discussion topic. You don't have to reply to my existing post. Okay, you can create a new discussion topic and answer from there. Okay. For those of you who have replied to my original message, it's okay. It's all right. I will read I will read your responses from there. But you, but if you want, or rather, if you should, just create a new discussion. Okay. Don't have to reply to my link. If you have replied to my link, that's also fine. Don't have to worry about it so much. Huh? Okay, very good. I see lots of responses coming in. I will just randomly pick a few. Okay, I'll just read randomly. Muhammad Ali Muhammad Al Ajlachi. Cortex A, application processor cores for performance intensive systems. Cortex R is for high performance cores for real time applications. And Cortex M microcontroller cores for a wide range of embedded applications. Okay, good. Thank you. Let's see. Random choice. Okay, Nur Iqmal Hakim, Cortex A for application processors, providing a range of solutions for devices that do complex compute tasks. Okay, Cortex R, range of processor optimized for high performance, hard real-time applications. Okay, good. Cortex M, smallest, okay, the smallest or lowest power processor for discrete processing and microcontrollers. All right, good. Okay, if you can keep the responses coming. I have not. I don't see a summary of how many discussions that are in, but if you are still responding, please continue to do so. I will then continue the slide deck. Muhammad Ali, if I've pronounced your name wrongly, I'm sorry. This is the first. It's the first time I'm pronouncing your name. So if it's wrong, please correct me. Thank you. Okay. So in summary, the the three abbreviations, Cortex A, Cortex R, and Cortex M, okay, they have a particular meaning. So the Cortex R are usually for real-time and safety critical applications. The Cortex A, the A stands for application. So that's why if you notice, many handphones, maybe mobile phones use the Cortex A processors. Why? Because they are more for applications. Okay, so they run the OS, they run the various applications on a mobile phone. And then the Cortex M are more for microcontrollers, the mobile kind of devices, and yeah, for microcontrollers, right? So good. So
Like
that covers. Sorry.
Like remote, like drones, for example. I'm
Maybe
controlling something that
drones.
is.
Yeah, maybe drones or appliances. I've been using washing machines a lot. Maybe there are also other devices that require microcontrollers. So Cortex M are more for for that particular purpose lah. Okay.
Understood.
Yeah. Okay. Good. Okay, so that covers our section on computer evolution. Now I will now talk about something other than processors itself. Okay, basically the earlier sections we were always talking about processors, their function, their structure, the evolution, how many bits, what are they used for, and so on and so forth. Now let's move into a discussion of something a little bit higher level. Okay, a little bit higher level. We don't want to talk about the processor anymore, but we talk about cloud, something that we don't see physically, but yet we use it as if we are using an actual machine. Okay, so in this next section, we're going to cover a little bit about cloud computing. Okay, I'm sure many of you have heard about cloud computing. So basically, it is internet related. Okay, it's an internet related infrastructure, and it enables and it allows a wide variety of services. Okay, it is ubiquitous, meaning you can use it anywhere, anytime. Okay, it is convenient because it is ubiquitous, because it's everywhere. You can use it on different devices even. Okay, um, the anytime part is also meaning that it is on demand. It's anytime that you need it, you can gain access to it. And the interesting thing is also it is a shared pool. That means nobody actually owns a particular machine, but everybody gets a chance to use it anyway. Okay, why? Because all these computing resources are put on the internet for different people to use, for different purposes, and for different platforms and whatever. Okay, so it's a really a very abstract way of using computers lah. Okay, now there are three main cloud-based services. Okay, the first one here is software as a service. Okay, notice that everything on the cloud is a service. Okay, why? Because the service provider, the so-called service provider is giving the user a service. They don't give you a product or something like that, but rather they give you a service. So the first one here is software as a service, right? And an example of software as a service are those applications that are running on the cloud. Okay, all the Google applications like YouTube, Gmail, Flickr, what else? All the various Google applications okay, those are cloud-based services because you are going to access those services using your browser. It's on the internet somewhere. Okay, contrast that to your traditional email client that you have to double click in order to run the application for you to retrieve your email. Now, those are not on the cloud. Those are applications running on your computer. Okay. But for example, Gmail, you don't have to double click on an application on your PC in order to retrieve your email. You just go to a browser and you log in from there, and then your email is there. Okay. So Gmail is a software, or rather an application service that you access on the internet online. Okay. Similarly, the Microsoft Office 360, what you are getting as a USM student, your email, your Microsoft Word that is online, Microsoft PowerPoint that is online, those are software as a service. Okay, Dropbox is also another popular cloud-based storage, right? Okay. The next one here is platform as a service. Okay, platform as a service acts as a toolbox lah, especially for developers that you want to develop software applications and to be able to deploy it online. Okay, that one is what we call platform as a service. Later, you might some of you may already know, or some of you may later make use of platforms such as Windows, Azure, Google App Engine. These are available again online. Okay, online for you to develop applications and software or whatever. Okay. The third service here is infrastructure as a service. Now, infrastructure as a service allows you to have the processing power, the storage power, and also the networks. Okay, that is available online as well. So that means if you want access to processing power, access to storage, and all this network-related kind of service, you are using the cloud service in form of the infrastructural perspective. Okay, not the software, not the platform, but you want to use the infrastructure itself. Okay. So again, Windows Azure again provides some infrastructure service as well. Google Compute Engine, Amazon Web Services, and so on. So these are some of the examples of services for the infrastructure perspective. Okay, all right. So okay, let's look at the chat box a little bit. I will try to see whether I can answer some of the questions. Are ARM processor directly soldered onto the motherboard, like unlike swappable desktop computers? Yeah, probably in that sense. Okay, that means ARM processors are already inbuilt into the microcontroller or whatever, and it's not something like, oh, you can just take out and put in, take out and put in kind of thing. Yeah, that's right. The C panel, I'm not quite sure what you mean. IaaS like iCloud, infrastructure as a service like iCloud. I'm not sure about this one. If anybody knows about iCloud, maybe you can help respond to Ali. All right. Virtual machine. Now, this virtual machine, sometimes you can actually deploy it on your desktop as well. So VMware may or may not be actually something on the cloud. Okay, so yeah, there are many different varieties of VMware that you can play around with. Okay, we have a little bit more time, so I think I will try to finish off the last section so that on Friday we can already move into a new topic. Okay, there's one more question here. What's the difference between infrastructure as a service and platform as a service? Okay, as I was mentioning to you, the infrastructure as a service focuses more on the processor capabilities, the storage capabilities, whereas the platform as a service is more for developing components, developing software, and then you run it on the cloud itself. So the platform as a service is something like something a bit higher level than application, whereby the programmer goes into the platform as a service to develop applications. Okay, so that's the main difference there lah. Which is better, in premise or cloud computing? In premise, I assume that it is your own machine, is it? As compared to cloud computing. Well, I suppose it depends on what you want to do. But put it this way, lah, you can't run away from having your own hard machine. Okay, but what you do with your hard machine, again, some of it you want to use it without the cloud, and some you want to use it with the cloud. If you are constantly traveling and you don't want a very high performance machine, then of course cloud computing is very good. That means you just carry a lightweight machine with just a simple browser, and then from there you can do everything. You can access your email, you can type your Word document and whatever. But if you do not have a good internet connection, then you have no choice but to actually use your own so-called, in your own words, in-premise machine to do some of the processing with you, and then later upload to the cloud. So I think maybe, in my opinion, both are needed depending on your needs lah, basically. Okay. Okay. The last section also I will breeze through very quickly, but I will highlight certain things that are more important and maybe certain things that are just useful for knowledge only lah, but don't have to worry so much about it. Now, performance issues basically talk about some numbers, some metrics, some measurement as to know whether the machine, or how fast the machine is processing, and so on and so forth. Okay, so in terms of performance assessment, we talk about, let's say, cost, size, speed, and things like that, power consumption, reliability. All right, so these are some of the key parameters. But maybe at a very, very basic level, most computer person will be interested in the clock speed. Okay, clock speed, and this is measured in hertz lah. Okay, hertz. Well, hertz is actually a physics measurement for the vibration, but in terms of computers, the clock speed refers to how many cycles per second the processor works. Okay, cycles per second. So from the hardware point of view, the computer has, or rather the processor has a quartz crystal that vibrates, and then of course that is analog. But there will be a conversion. There will be a conversion to make everything digital. So the voltage should be either high, low, high, low, high, low, high, low kind of thing. And when the voltage goes high, low, high, low, high, low, that is the cycles, the cycles of the clock. Okay. So in terms of computer processing, one of the measurements that we are interested in is the cycles per instruction. That means every time a computer processes one instruction, very often the computer needs more than one cycle to finish processing one instruction. Okay, so one instruction may be broken up into, let's say, 8 parts, and each part needs one cycle. Okay, so in this case, you need 8 cycles to complete one instruction. Okay, now what if you have many instructions? Some instruction needs 8 cycles. Another instruction needs only 6 cycles. Another instruction needs 10 cycles. All right, so you have different instruction that needs different number of cycles to complete. So what you need to do is you add up all the cycles. Okay, so if you look at this, if you look at the formula here, the cycles needed for each instruction, you add them all up. Okay, and then you divide by the total number of instructions that you have. So on average, you get the average number of cycles per instruction. Okay, so that is cycles per instruction. It's one of the popular measurement lah. Okay. Another popular measurement is millions of instructions per second. That means, so of course, one instruction requires a few cycles to finish. Okay, that is cycles per instruction. Now, how fast can the processor process the instructions? Okay, so as I was mentioning to you, one other popular measurement here is millions of instructions per second. In 1 second, how many instructions can the processor process? Okay. All right. So here the formula says I over t multiplied by 10 to the power of 6. So it's the number of instructions per second. So it's instructions I per second. Okay. And then you divide it by 10 to the power of 6 to get the millions of instruction. Okay. So that's the basis of that particular calculation here. Another way to express millions of instructions per second is frequency divided by cycles per instruction. Then again, you divide by 10 to the power of 6. Okay. Now, how to get this f? How to get this f over CPI times 10 to the power of 6? So if you notice, f is actually cycles per second, correct? F, remember, is cycles per second, frequency, cycles per second. You measure in hertz, right? So the f there is cycles per second. And if you also notice, this cycle divided by cycles per instruction is actually the number of instructions, isn't it? Okay, the total number of cycles, if you divide it by cycles per instruction, you will get the total number of instruction. Okay, so if you notice the working on the right side of the screen, that will then take you back to the I per t times 10 to the power of 6. Okay, don't worry if you cannot appreciate this immediately. Maybe the tutorial questions will help. Okay, because next week we're going to start some tutorial already. All right. Some of the tutorial questions will be discussing this MIPS formula. Okay, the millions of instructions per second. So yeah, maybe you can sit down, try to appreciate the formula, and then see how it works out. Yeah. Okay. I'm not expecting you to understand this immediately, but don't worry. We will work it out together later. Okay. Good. The other thing that we need to be aware of is the benchmark. Benchmark meaning, how do we decide whether one processor is better than another processor? Okay, so we need to have a certain standard set of testing data in order for us to test all the different processes lah. Okay. So there are various standards organization which come out with a standard set of data to pump into the computer and let it process and then see how fast they process something. Okay. So like for example, this particular organization, System Performance Evaluation Corporation, they came up, I think the latest one for computation is the CPU 2017 test set. Okay. So this one that tests the floating point processing and also the integer processing and all that. So they came out with all these standard sets. And then they will measure the speed and see how fast the different processors process all these data lah. Okay, don't worry. We don't need to know the specifics of all this. Just be aware that processes are measured in terms of certain standard benchmarks lah. And then for all those benchmarks, they use certain metrics. Okay, so again, don't have this one. Don't have to worry so much. You just be aware that there are some calculations needed. Like for example, in this case, 12 integer benchmark data. They're just gonna pump it in and then calculate. So, but don't worry. Don't have to know much in detail. Just be aware that there are certain calculations made. Okay, right. And ultimately, also the performance of the machine, the speed of the machine, is dependent on a few things. Okay, now we think that the more processing power you have, the faster the processing will be. Okay, so we assume that the speed up of the machine is dependent on the number of processors, maybe. Okay, so let's say one core, dual core, quad core, octa core, or whatever. The more cores you have, you think that it's going to be double, but that is not necessary. So okay, usually speed is bounded by certain conditions. All right. Now let's look at this particular formula, Amdahl's law. So it says that the speed up is dependent. Okay, how to calculate speed up in the first place? Speed up is calculated by the time that is needed to run the program on a single processor. Okay, on a single processor. Divide by the time to execute on n number of processors. Okay, n number of processors. But the thing is, the code, the instruction, some of it can run in parallel, some of it cannot be run on parallel. Okay, so if all the instructions can be run in parallel, that means your f, okay, the f is very big. Okay, it's very big. And therefore, if you look at the formula here, if your f is, let's say, 1 is the biggest lah, okay, the 1 minus 1 will become 0. Okay, and what you have is the speed up will be n. Okay, the speed up will be n. So if your code is totally parallelizable, then your speed up will be dependent on the number of processors that you have. So if you have 2 processors, the speed will double. If you have 4 processors, the speed will quadruple. Okay. However, if you have infinite number of processors, your speed up will then be dependent on the amount of parallelizable instruction that you have. Okay. So bottom line is, speed up is dependent on how much your instructions can be parallelized. Okay. If your instruction only can go one by one, then it doesn't matter how many processors you have. It's useless. Okay, because it has to go in one by one. But if your instructions can be broken up into many channels, then the many processors can process all those instructions together, and then only you can gain that speed up. Okay, right? Question in the question box. What does it mean by parallel? Now, parallel means at the same time. Okay, let's say for example you have 4 instructions and 4 processors. Okay, now if those 4 instructions are not dependent on each other, so that means I can run instruction 1 separately from instruction 2, and I can run instruction 2 separately from instruction 3, and instruction 3 I can run it separately from instruction 4. So all those 4 instructions they don't depend on each other. Okay, so therefore, if I have 4 processors, I can then process all those 4 instructions in parallel at the same time to each of the processor. Okay. But if those 4 instructions cannot be done in parallel, meaning they are dependent on one another, because maybe the second instruction is waiting for the output of the first instruction, and maybe the third instruction is waiting for the output of the second instruction, and the fourth instruction is waiting for the output of the third instruction, correct? So all these cannot be done in parallel because they are waiting for each other. So instruction 1 has to go first, then only instruction 2, then only instruction 3, then only instruction 4, right? So if you have 4 processors, all these 4 guys cannot go together because they're waiting. So what happens? They have to go sequentially. And you only need one processor to process because they're all in sequence. So the other 3 are actually useless. The other 3 processors will be useless. Okay? So that's what I mean by instructions in parallel and instructions that are not in parallel. Now, this one, speed up later, we will discuss it later in the topic on CPU. Okay, Dr. Mamit will cover the issue on speed up. But now I introduce it to you first. Okay. Right. So just very quickly, in the chat box again, a dual core processor is not necessarily faster than a single core processor. True or false? Why? Okay, just very quickly in the chat box. Okay. Okay, very good. I can see some very quick answers. I think a majority of you say that it's true. Okay, dual core processor is, yes, not necessarily faster than a single core processor. Okay, so majority of you say true because if it's not parallel, then it will be the same. Yeah, correct. Okay, if your codes are not parallelizable, then dual core, single core, it's still the same. Okay. Some extreme situations can also be true. Let's say, for example, if we have a dual core machine and those are very slow dual core machines, okay, very slow dual core machines. So, but if you have a very and your single core processor is a very fast single core processor, okay, in those cases, it might be also true that your single core processor might still be faster than your slow dual core processor. That can also be true. Okay, but yes, majority of you indicate that due to the parallelization of the instruction, that makes the difference. Okay, which is true. Yeah. Okay, very good. I think a majority of your responses is true because of the instructions. Yeah. Okay, good. Thank you very much. Okay, we're almost done. But before you go, I just want to just share some more slides, which is also available for you to copy from eLearn. Some additional materials. So you can read up about the Intel machines, IBM machines, PowerPC machines, and all that online. Okay. And if you're also interested to read up about the ARM processor and also the various benchmarking and also instruction sets. You know, some manufacturers, they release their instruction sets. Some of it you can actually read from the manufacturer's website and all that. Okay. Okay. If any questions, you can post them on the chat box. Otherwise, today I won't post any reflection, but I'm going to release a very quick quiz. Okay, a very quick quiz. Now, this quiz will only be for 3 minutes because, I mean, that means when you start answering the quiz, after 3 minutes, time's up. Okay? After 3 minutes, time's up. There are only 5 questions, multiple choice. Okay, multiple choice, 5 questions. Okay, but it will only be for 3 minutes. After 3 minutes, your attempt will be finished. Now, after you have answered all the 5 questions, please make sure you click on the button to submit all your answers. Click on the button to submit all the answers. Okay, all right. I will make the quiz available. I'll make the quiz available now. You just give me a minute. I will activate it on eLearn, and I will also give you the link on the chat box. Just give me a minute. Okay, the link is already activated. You can see the link on the chat box and also the link on eLearn. So please try the 5 questions. You're given 3 minutes to try. Once you have finished the quiz, that is the end of the lecture today. I will see you on Friday morning. Okay. So thank you very much. Enjoy the quiz, and I will see you Friday. I will also post the attendance link again. So those of you who haven't recorded your attendance, please stay back a little while. I'll give you the link.
Doctor, the quiz. When is the deadline of the quiz? Is it available for an hour or so?
No, it finishes at 3 o'clock. So you better start now.
Okay, thanks.
Okay, some of you may be a bit, might only start a little bit later. I've extended the due date of the quiz to